Alright, let's continue. Okay, let me open the table of content first. Alright. We are on chapter 18, patching introduction here. The last time we are on this section, patching also too slow. And now we will take a look at this section, a memory trace. Let me open that. Okay. Before we continue to the memory trace section, previously I'm kind of confused with these two problems that this paragraph talking about, and it looks like the problem is, what is it? Okay, the page table might be too big, I assume, something like that. Too big. And the second one is what is it called? This one, extra memory reference are costly. So using a page table might be too slow, I guess. Maybe the two problems that we are talking about here is this two. The page table might be too big, and then using page table might be too slow because extra memory reference, I guess, something like that. Okay, now let's continue into this section. Before closing, we now trace through a simple memory access example to demonstrate all of the resulting memory access that occur when using patching. Trace through a simple memory access example to demonstrate all of the resulting memory access that occur when using patching. The code snippet in C programming language in a file called array.c that we are interested in is as follows. This one, and then using for loop here. If I understand correctly, basically we are putting 0 in each array element. Okay, we compile array.c and run it with following command. Right. Wait. Is this uppercase O? What is uppercase O means? Is that optimization? Looks like it. It looks like we are using some kind of optimization here, using this uppercase O flag. Oh, interesting. Okay, I mean this one is for the, what is it called? Executable name, right? This one, and then this one for the warning, something like that. Of course, to truly understand what memory access this code snippet, which simply initialize an array, will make, we will have to know or assume a few things. First, we will have to deassembly the resulting binary, okay, using object-dump on Linux or OTool on a Mac to see what assembly instructions are used to initialize the array in a loop. Here is the resulting assembly code. Wait, let me try. This one is chapter chapter 18, okay. And then what is it? Array.c. Okay, looks like we didn't print anything. Alright then, something like this. Okay. Alright. Okay. Maybe use something like this, I guess. Array, and then divide that by the array element. Then like this. Before this one, let me try stdio. Okay. Wait a minute. Just to make sure that the calculation is correct, I guess. Right, the CPP in here means the C preprocessor, not C++. In case anyone knew. Chapter 18, okay. Right, I have this one. Now let me compile that. Alright, and it looks like we are using some kind of optimization with this uppercase O, right? Test uppercase O flag. Unused variable I, okay, right. statement with no effect already. Yeah. Okay, something like that. And then we are using object term. I think I've used this previously, but still not sure how to read the information from the object term here. Let me try. Pipe test tool list. Oh, okay. Option and file. So we need to provide the option. Maybe this one. The disassembly, right? Okay. Interesting. $1,024. Is this one? So there is init, assembly, and then .text section, I guess. Oh, wait a minute. What if I remove that? Is there any effect? XOR? That's not exactly the same, but maybe. Maybe it is similar. I am still not sure. The code, if you know a little about x86 assembly, which unfortunately I don't yet, at least is actually quite easy to understand. Let me read the footnote first. We are cheating a little bit here, assuming each instruction is 4 bytes in size for simplicity. In actuality, x86 instructions are variable size. Oh, okay. The first instruction moves the value 0, sound as this one. Okay, value 0 into the virtual memory address of the location of the array. This address is computed by taking the contents of a D register, I assume this one, the content of a D register, and adding the EAX register multiplied by 4 to it. Oh, interesting. Yeah, it's quite different. Multiplied by 4 to it. I think this one, right? So I assume from this assembly instruction we move the value 0, right, into this. Oh, into the location of the array, and then to get the location of the array or the memory address of the array, we do this calculation. I'm still not sure what in add the register here, but we add this add the register into EAX register and then multiply that by 4. I'm assuming 4 in this case mean 4 byte. The what is it called? The size of integer in the machine. If we take a look, print size of int, that is 4 byte. The size of integer is 4 byte. So I assume that we got 4 in here because of the integer size of the array element. So okay, maybe this is the base address, something like that. The base address and then adding the maybe something like this, base address plus virtual address multiplied by size of int, the size of integer type, something like that. Maybe this is what it means. So we are moving the value 0, which is this one, into each of the array element. Maybe something like that. I'm assuming this is what happened in this assembly instruction. Okay, those at the register hold the base address of the array. Oh, okay, the register hold the base address of the array, whereas EAX hold the array index. Oh, okay, the array index or offset, I guess. So maybe array index we multiply by 4 because the array is an array of integer, each of size 4 byte, right? The second instruction increment the array index held in EAX. Oh, increment, okay. I thought that this is include, but looks like this mean increment. Okay. The second instruction increment the array index held in EAX register, and the third instruction compares the content of that register to the hex value this one or decimal 1000 if the comparison shows that two values are not yet equal. It is what GNA instruction test. Okay. So this means that we are comparing that. We are comparing 1000 with the index in the array. And if the comparison shows that two values are not yet equal, it is what the GNA instruction test. The fourth instruction jump back to the top of the loop. Okay. What the GNA instruction test? Isn't GNA just jump instruction? We are jumping back into this one. So why is it the GNA instruction test? Yeah, I'm still not sure about the GNA instruction here. I thought the testing in the GMPL here. We are testing if the index equal to 1000, right? If it is equal, if it is not equal, then we are jumping this one. Oh, maybe GNA stand for jump if not equal. Jump if not equal, maybe something like this. I'm not sure. So maybe that's what it means. That the GNA instruction test. So we are testing if the result of GMPL equal or not in the GNA here. If it is not equal, then we are jumping back to this. Okay, maybe this is still assumption that can be wrong, I guess. Alright. To understand which memory access this instruction sequence make at both the virtual and physical level, we will have to assume something about where in virtual memory the code snippet and array are found, as well as the contents and location of the page table. Which memory access this instruction sequence make at both virtual and physical level. This instruction sequence make. Okay. We will have to assume something about where in virtual memory the code snippet and array are found. Assume something about where in virtual memory the code snippet and array are found, as well as the contents and location of the page table. Okay, so there are two assumptions here. Where the code array in memory, some I guess. Okay, and then the content and location of the page table, something like this. Okay, for example, we assume a virtual address space of size 64 kilobyte, unrealistically small, right? We also assume a page size of 1 kilobyte. Okay. Virtual address space size is 64 kilobyte, and then the page size is 1 kilobyte. All we need to know now are the content of the page table and its location in physical memory. Let's assume we have a linear array-based page table and that is located at physical address 1 KB. Okay, yeah, maybe this is more like this because we are using the binary representation, I guess, rather than the decimal representation. Okay, and the page table located at physical address 1 KB. Okay, page table located in physical address. Okay, 1 KB. Maybe something like this. As for its content, there are just a few virtual pages. We need to worry about having map for this example. First, there is the virtual page the code live on. Because the page size is 1 KB or kilobyte, virtual address 1024 resides on the second page of the virtual address space. Just a few virtual pages we need to worry about having map for this example. There is the virtual page the codes live on. Okay, because the page size is 1 kilobyte. To address this one Wait, it is located at physical address 1 kilobyte. Is it the page table address? As for its content, because the virtual address 1024 resides on the second page. Resides on the second page of the virtual address space. Okay, I'm assuming the first virtual address space already taken up by the page table, maybe something like that. Virtual page number equal 0, as virtual page number 0 is the first page, right? And I'm assuming the first page already taken up by the page table, so we are using the second page of the virtual address space. Let's assume this virtual page maps to physical frame 4. Virtual page number 1 mapping to the page frame number 4. Okay. Next, there is the array itself. Its size is 4000 byte. 1000 integer. Okay. Write one integer in this. What is it called? In this scenario is 4 byte, right? So when we have 1000 integer, we need 4000 byte to store this 1000 integer, something like that. And we assume that it resides at virtual address 40,000. Oh, hello. I cannot read your username. Hello, welcome. What code editor do you use? I'm using Vim. Is anyone wondering? Yeah, Vim. That one. Is Vim having? Yeah, this one. VI improve. Okay. We assume that it resides this, what is it called? This 4000 byte of data reside at virtual address 40,000 through 44,000. Okay, virtual address 40,000 through 44,000, not including the last byte. Okay. The virtual page for this decimal range are virtual page number 39 until virtual page number 42, I guess. Okay. Thus we need mapping for this page Let's assume this virtual to physical mapping. For example, virtual page address 39 to page frame number 7, virtual page address 40 to page frame number 8, virtual page number 41 to page frame number 9, virtual page number 42 to page frame number 10. Okay. Something like this, I guess. Figure 18.7, a virtual and physical memory trace. Okay, we are now ready to trace the memory reference of the program. When it runs, its instruction fetch will generate two memory reference, one to the page table to find the physical frame that the instruction resides within, and one to the instruction itself to fetch it to the CPU for processing. Its instruction fetch will generate two memory reference. Oh. Two memory reference. One to the page table to find the physical frame that the instruction resides within, and one to the instruction itself. To the instruction itself. Physical frame that the instruction resides within to fetch it to the CPU. So we are fetching the instruction from the physical frame, I assume, and then one to the instruction itself to fetch it to So we get the instruction from the physical frame, and then we give those instruction to the CPU. Is that it? But why is it to memory reference? I mean, one reference is for the instruction where the instruction reside, right? But this one is something that I'm still not sure. One to instruction itself to fetch it to the CPU for processing. To fetch it to the CPU. In addition, there is one explicit memory reference in the form of the move instruction. This add another page table access first to translate the array virtual address to the correct physical one, and then the array access itself. The entire process for the first 5 loop iteration is depicted in figure 18.7, page 11. This one, I guess. 39. Okay, maybe maybe these two memory reference in this case mean that the first one is the virtual memory to get the physical frame address, something like that, and then the second one is the physical frame address or physical memory address that we can use to give it to the CPU for processing. Maybe something like that. Like the first memory reference is the memory address to get physical memory address, and then the second one is physical memory address itself to put it in the CPU for processing. Maybe something like this. Yeah, I'm still not sure yet. What is the two memory reference being generated with its instruction fetch? And then why we have this what is it called? Different page table, I guess. Memory access. Yeah, what this mean? Page table 13.9, page table 1. Is it the let me check first. Page table 1. Oh, I assume the page table or maybe the virtual page number. This one maybe means the virtual page number 1, and then this one virtual page number 39, maybe something like that. And then virtual page number 1 consists of the instruction code. So we get the code from here, right? To get the instruction here, and then this one page, what is it called, virtual page number 39, where we store the result from the page number, from the instruction, I mean. Again, this one, right? The virtual page start from page number 39 until 42. 39, 40, 41, 42, and why is it another one? 39, 40, 41, 42, and there's extra 43 here. Okay. Okay, we are filling with 0, I guess. For the first 5 loop iteration. Okay, I assume we have 5. Oh, 1, 2, 3, 4, 5. Wait a minute. Is this just virtual page number 39? Or what is it called? The page table entry 39? Something like that? So how do we divide this page number, the virtual page number? Right, we have 4,000 bytes, right? How do we divide the integer between these 4 page number? Maybe that is what happened here. Until we fill up this page number 39, we will keep adding that here in the page entry table 39, page table entry 39, maybe something like that. And this is the code. Okay. Address. let's continue analyzing this figure 18.7 on the next session. So I guess that's it for now. Thank you for watching and see you next time. Bye bye.